All right, so let's talk about ionic compounds, ionic bonds, and then we'll talk about metals, and then we'll get back to our covalent, okay? So ionic compounds, right, we know that we have to use our Coulombic forces to interpret the strength of their interactions, okay? So first off, let's make sure that we know how to figure out what our ionic compounds are going to be. So if we have a charge of maybe, if we have magnesium plus 2 and we have nitrogen minus 3, right, we have to create an ionic compound. We take this 2, we go down, we take the 3, it goes down, and our compound has to have an uncharged, or has to be not uncharged overall. So we would have Mg3N2, and this is going to be an uncharged compound, okay? And this is going to be an ionic compound because we have magnesium, which is a metal, and nitrogen, which is a nonmetal. So we're going to say that this is going to be an ionic compound. So how strong is that interaction? We are going to use Coulombic forces to understand it. Okay, so Coulombic forces, right, we have charge 1, charge 2, divided by the radius squared. So if we have higher charges, we're going to have a stronger force that's holding them together, right? So if we have charges that are higher, right, our force is going to be stronger. So if we compare this to a different compound that maybe had a +2 and a -1, we would expect for this interaction to be stronger than than the +2 and the -1 because there is larger charges here. It also, of course, depends on the radius. So if we have larger ions, right, larger distances than in between those ions, we make this number larger, it's squared even, so that bottom gets larger, our force then is going to get smaller, okay, because it's on the bottom there. Okay, so larger charges equals stronger interaction, and larger distances is going to equal a weaker interaction. Okay? Overall, the ionic crystal, really what we have to have happen, it's going to maximize attractive forces and minimize the repulsive. Okay? It's just the same as up here when we were talking about our nuclei interacting versus the nucleus and the electron cloud, right? Nucleus, electron, cloud, that's an attractive force. Nucleus, nucleus, that's repulsive. On our ions, it does the exact same thing, right, with our ionic compounds. It's just that now we have full negative and full positive charges because it completely steals that electron, okay? But our overall charge for our compound has to be equal to 0, all right? So I'll put that over here too. Charge equals 0, okay? All right, so now when we start to talk about our metals and our alloys, right, what we're going to start to talk about is really, we need to kind of understand the particle diagram for this, okay? So with our ionic compounds, our particle diagrams are pretty easy, right? We've got positive, or maybe our magnesium here would be 2+, our nitrogen is going to be a 3-, we've got 2+, a 3-, and a 2+, right? This would be our particle diagram for our Mg3N2, right? Easy. Our metals gets a little bit weird because our metals, right, They kind of like having the electrons, but they don't really care. So oftentimes what we're going to do is we're going to draw our nuclei, or draw our atoms, and we're going to have just a sea of electrons that are in between, okay? So maybe this is an iron atom, we say, and then these are the electrons, the sea of electrons that are in between. So these are our positives, and then we've got our negatives that are kind of just freely moving in between, okay? But we have two different types of alloys here, okay? So this is going to be our general kind of metal particle diagram, but we have two different types of alloys. One type is an interstitial alloy. And interstitial means in between the space. So it's really, the alloy is when we have our positives, right? What we can do is we can take and put a different element in the spaces in between. So maybe we put a copper atom in the space in between these other atoms, okay? So maybe it's iron and copper, something like that, right? That would be an interstitial alloy because the copper is taking up the space in between the original atoms. The substitutional alloy is a little bit different, okay? It is where we substitute some of the atoms for something else. So maybe I still have some of my original positives, but I substitute it with a copper atom, okay? And this depends on the size of our different atoms, okay? It depends on the size of the elements. We wouldn't have to necessarily know, but we should know this vocabulary, okay? All right, so next up we're going to be talking about covalent compounds.